So here's the question. A person going in a car which is moving with respect to ground with speed 3c by 5, okay, speed 3c by 5, throws a ball in upward direction. Throws a ball in upward direction with speed c by 2. Speed c by 2. What's the speed of the ball with respect to ground? What's the speed of the ball? What's the speed of the ball with respect to the ground? Okay. So let's still use the same kind of notation that we were using. Okay. So we are asked to find the speed of the ball with respect to ground. Okay. Here it's just said that it's thrown in a direction, in an upward direction with speed c by 2. Right. So we say that this is the speed of the ball with respect to the car. Okay. This is the speed of the ball with respect to the car. This is the speed of the car with respect to the ground. Right. So let's use this transparent notation. Later on, we'll use the prime thing, all right, just to get the physics clear. Okay. So what we have here, we'll write it like this: the velocity of car with respect to the ground, and it's along the x-axis. Okay, it's given us 3c divided by 5. Okay. 3c divided by 5, right? And what's the velocity of the ball with respect to car? Right? It says that it's in the upward direction, so we only have the y component. We'll write it like that. Okay, I hope there's too many indices, but let's just write it like this. Okay, so velocity of the ball with respect to car, it has only y component. So, or we can write it as a vector if you like. Okay, you can write it as a vector. Velocity of the ball with respect to car, that's equal to c by 2 y cap, right? Okay. And we are asked to find the speed of the ball with respect to the ground. Right? The question is this: what is speed of the ball with respect to ground? Okay, what is this? That's the question. And you are asked actually the speed, so you have to take the velocity and square and add the components in order to get the magnitude. Okay, that's how we do this. All right. Now, now we can so we can write this in component form. All right. See, we have taken this car with respect to ground is along the x direction. We'll take that this is along the x direction. All right. And the ball, velocity of the ball with respect to car is along the y direction. That's given in the question. We need to find the speed of the ball with respect to ground. Right. So how do we do this? Let's put a vector here. Okay. So we can easily write this equation: velocity of the ball with respect to the ground. Okay, the x component of it, right? The x component of it. I hope this is fine. What would this be? Okay, we need to find the velocity of the ball with respect to the ground. So you would have the velocity of car with respect to ground, and you would have the velocity of the ball with respect to ground divided by 1 and VCG VBG by c square, right? And you have to tell me whether it's a plus or minus over there. Okay, we are talking about the x component. So we will have the x here and velocity of the ball with respect to the car. Velocity of the ball with respect to the car. Just give me a moment. Right? We need to find velocity of the ball with respect to ground, the x component. So what we know is the velocity of the ball with respect to the car. Okay. Right. Velocity of the car, and then you would have VBC VCG. Okay, you're talking about the x components. I'll put an x here divided by c square. All right. These are the things involved here. So you tell me whether it's a plus or minus over there. Okay. Tell me whether it's a plus or a minus over there. Right. In this case, it doesn't matter because we know that. All right. We can just let's put the velocity addition form, right? Let's put the velocity addition form, right? So we are asking the velocity of the ball with respect to ground, the x component of it, right? So it would include the velocity of the car with respect to ground, okay? And the velocity of the ball with respect to the car, okay? So the ball has a velocity with respect to the car, and the car has a velocity with respect to the ground. So you just have to add them when you are looking from the ground, right? So what's the velocity of the ball with respect to ground? You just have to add. It's just like, yeah, throwing a ball from a train. If you are looking from outside, Okay, if you're looking from outside, what you see would be the sum of this velocity. Right? Train is moving with velocity v1, the ball is moving with respect to train with velocity v2. Then when you look from the ground, the ball will have velocity v1 plus v2. Okay, that's a Galilean addition. Right? It's the same concept here, except that there is a correction term over there. Right? Except there is a correction term over there. Is this clear? And anyway, the velocity of the ball with respect to the car, the x component is 0. So this is simply velocity of car with respect to ground. This is obvious, right? This looks like the ball is sitting at rest in the car, right? So with respect to the car, it's not moving. So what you are looking at is that the car is moving like that and the ball is sitting there. Okay. So what's the velocity of the ball with respect to ground? It's the velocity of the car with respect to the ground, right? So that's fine. Okay. And what was that? That's equal to, magnitude is equal to 3c by 5. All right. So we easily got the x component. All right. I just wrote down the equation. All right. You could have written it without that. So velocity of the ball with respect to ground, x component is 3c by 5. Is this fine? Is this all right? Okay. This is obvious, right? Because the ball is sitting at rest along the x direction. It's moving. It's at rest along the x direction. So, so we have got that. Shouldn't have removed that. Okay. Right. So what were things that we had here? I'm sorry. We have got velocity of car with respect to ground, this 3c by 5, and velocity of ball with respect to car, y component is c by 2, and velocity of ball with respect to car, x component is 0. Okay. Velocity of ball with respect to car, z component is also 0. We are talking about the xy plane, so let's not worry about z. So we used this and we found the x component of velocity of ball with respect to ground. Okay. The next thing is we need to find the velocity of the ball with respect to the ground. Okay. Y component. What's the y component? Right? What is the y component? Okay. We know that this involves velocity of the ball with respect to car, y component, multiplied by square root of 1 minus v square by velocity of car with respect to ground square c square, divided by the same factor, 1 plus the same factor, right? In the velocity addition, the same factor comes up. Am I right? Even though you are adding transverse velocities, the denominator is the same. Right? And this term is 0. This term is 0, right? Okay. So this term is 0, so this is 1. So this is just this. All right. And this is given, right? The velocity of the ball with respect to the car, y component is given as c by 2. Am I right? Is c by 2? Yeah, c by 2. Okay. So this is equal to c by 2 square root of 1 minus velocity of car with respect to the ground. Velocity of car with respect to ground. Okay. That was what was velocity of car? 3c by 5, right? What was it? Yeah, 3c by 5. So this becomes 9 by 25. Am I right? Yes. That's a c square and c square, they get cancelled. Right? So this is c by 2 square root of 25 minus 9 is 16. All right. So 16. So it's become 16 by 25. So it is 4c divided by 2 into 5. Is that correct? Just take the square root. So that's 2c by 5. Okay, this is the velocity of ball with respect to ground, y component. Right? But you're asked the speed of the ball. You're asked the speed of the ball with respect to ground. So you have to take the components and square and add them. Am I right? That is v plus v bg y square. Okay, and you just square these things and add, you get this is equal to square root of 9c square by 25 plus 9c square by 25 plus 4c square by 25. Right. So the answer is that's equal to, this is 13. So the square root of 13 by 5 multiplied by c. Is this clear? Is there any question regarding this? Is this fine?
Okay.
All right. If you have any problem, all right, this notation will after some time we will use this primed notation. All right, we'll just use b prime u prime. Right. I wanted to use this notation just to be clear that you don't have to confuse whether it's a transformation or an inverse transformation. You just look at the physics and you know whether to put a plus or a minus there. It doesn't matter which one you put prime and which one you put unprimed. Right. So if you're just following the equations blindly, you may make a mistake as to which one to put there. Right? So you always have to think about the physics, what's going on, try to imagine it. What would be the total velocity if it's a Galilean law, right? If it's a Galilean law, think about it, whether it's a minus or a plus there, and then you'll have an extra factor for a relativistic thing there, right? And the transversal velocity, you always have to follow this. Okay? So that's why I put this notation, okay? And it may look a bit confusing because there are so many indices. After some time, we'll use the primed notation, and we won't really worry about whether which one is S or which one is S prime, or whether it's transformation or inverse transformation. We'll just look at the physics and realize whether to add it or not. Okay, is this fine? Okay. All right, and next one, okay, just to relax a little bit, we'll do a trick question. All right, this kind of questions can be asked. Okay, I already said it's a trick question. All right, so the question is this. Okay, let me think. Just give me a moment. Okay, let's see. Let's look at this question. Right. So we are given this question, right? Suppose A moves with velocity 0.6 c, right? Or we can put 0.9 c, doesn't matter. 0.9 c with respect to B. Okay. And also you see another object, C moves. Let's put it as plus, right? It means that it's along the plus x-axis. We're just talking about one dimension. And C moves with velocity, let's say minus 0.6 c with respect to B. Right? This is the question. Suppose A moves with velocity 0.9 c with respect to B, C moves with velocity minus 0.6 c with respect to B. This means that you have got B here, and this object A is moving at 0.9 c in this direction, and object B is moving at 0.6 c in this opposite direction. Right? Now the question is, what is the relative velocity? What's the relative velocity of between A and C as observed by B, What's the question? What's the answer to this question? Can you just think about it for a moment and give me the answer? So relative velocity between
addition u plus v divided by 1 plus uv by c square
അപ്പൊ നമുക്ക് കിട്ടുന്ന എന്താണ്? അപ്പൊ കിട്ടുന്ന ആൻസർ എന്താണ്? അത് എന്തിനുള്ള ആൻസർ ആണത്? വാട്ട് ആൻസർ ഇസ് ദാറ്റ്? റഫീഖ് ആണോ പറഞ്ഞല്ലേ? റഫീഖ് പറഞ്ഞ what did you say? You said that you just add this, right? 0.9c plus 0.6c, right?
അത് ടൈമിന്റെ ടൈമിന്റെ
മനസ്സിലായില്ല. ഇതാണോ നിങ്ങൾ പറഞ്ഞ ഉത്തരം?
അതെ അതെ അതെ.
Okay. Any other answer? So what's this answer actually? What's this answer? It's 0.9 plus 0.6 is, can we do this easily? It's 1.5 divided by, it's a bit difficult, right? Doesn't matter. Let's just say this is one of the options, right? You also may have an option like this, 0.9c minus 0.6c divided by 1 minus 0.9c 0.6c divided by c square, right? This also could be one of the option. The third option, okay, the third option is just this, it is 0.3c, okay, or simply like this, 0.9c minus 0.6c, all right? The fourth option is this, 0.9c plus 0.6c. This would be 0.3c and this would be 1.5c, right? Now this question is a very legitimate question. Okay, you can take as the option. If you just calculate this, you can put that as the option, right? So is it this, this or this? Give me one answer. Okay, so Rafiq has already said this is the answer. Am I right? Are there any other opinions about this? You can't see the board, can you? Sorry. If you are listening, I want you to answer this question. Okay, this is a very possible question. It's a possible question for the NET exam. Are there any other options? Is Jinsmon, can you guess an answer for this?
I think option C, sir.
Option
C.
C. Okay. Option C. So we have got two answers. Any other answer?
C.
C. Okay, so we've got two option A and one option C. Okay. Now I'll tell you why this is wrong. What is this speed? This velocity is actually the velocity of B with respect to A, right? Or velocity of A with respect to B. Am I right? Sorry, A with respect to C. What is this? What is this velocity? This is actually, what do we get here? This is the velocity of A with respect to C. This is the velocity of A with respect to C. Am I right? Rafiq, this is the velocity of A with respect to
C.
C. Am I right?
Yes, yes.
But the question is this: what's the relative velocity between A and C as observed by B? What's the relative velocity of A and C as observed by B? Right? That's the question.
1.5 C area.
Exactly. This is the correct answer. All right. It's 1.5 C. Right? The question is, what's the relative velocity of A and B with respect to B? All right. This is the velocity of A with respect to C. Right. This is some wrong answer. And this is also velocity of this is also relative velocity if they are moving in the same direction. Right. This is also the relative velocity if they are moving in the same direction. Right. Now, if you look at this, this is greater than C. Okay, this is greater than C, and this is allowed. All right. This is allowed. Now, so you have to use the velocity addition formula only if you need to find the velocity of A with respect to C, right? Relative velocity between two objects see, we are looking at two objects and we are just checking at what speed it moves away from each other, right? At what speed it moves away from each other. So this observer B would just see that they are moving away from each other at 1.5 C. There's no problem. It's a relative velocity, and it's relative velocity with respect to B. It's not the velocity of any object in any frame. All right, this is not the velocity of any object in any frame, so there's no problem with this. Even though this is greater than C, it's fine, all right, because this is not a real velocity of any object in any frame. It's just a relative velocity in some frame, all right? So this is the correct answer. Now, you may not immediately guess this because this is greater than C, and you see that, oh, greater than C is not allowed. Okay, but greater than C is not allowed if it's the velocity of an object with respect to some frame, right? If you are talking about the relative velocity with respect to some other frame, then this is allowed. This is there. Okay, so that is slightly a trick question. Right? You just have to add the velocity, and it can be greater than C. Is this fine? You have to remember this thing, all right? So if in such a situation, you use the velocity addition formula, instance velocity addition formula, only if you need to find velocity of A with respect to C. Okay, if you are asked the relative velocity with respect to something else, then this is the answer. Right? If they are moving in the same direction, right? If they are moving in the same direction, it would be 0.3 C. But I said that they are moving in the opposite direction, so you just have to add them up. Is this clear?
Yes.
Yes, sir.
Okay, good. And this thing is usually not discussed in textbooks, all right? It's also a bit confusing because we completely focus on the fact that nothing can move faster than c. And when we see this 1.5 c kind of thing, then we are a bit worried. Okay? We are uncomfortable when we see that the velocity is 1.5 c. It's a bit worrying. It is greater than c, and we don't like it, and we automatically may avoid this answer. Okay, but remember that this thing in this case, it's not a velocity of any object. It's just a relative velocity, right? It's true that no object can travel faster than speed of light. Okay. Okay, shall we do one more? Okay, this is a slightly more involved exercise. Again, another kind of problem using velocity addition. All right. A person going in car is moving with respect to ground with. Did we just do this thing? Okay, a car is moving with respect to ground along the plus x direction. Right now, I'm not using that BC notation. I'll just use the primed notation because I hope you know how to think about it physically. Right? So let's do this. A car is moving with respect to ground along the plus x direction with speed c by 2. Right? So we have got v is equal to c by 2. What is v? It's the speed of the car with respect to ground. Okay, that's a car with respect to ground. I'll use v. Right? And velocities of objects, I will use u. For velocities of objects, I will use u. Right? So we don't have to deal with so many indices. Right? So if you, okay. All right. V is equal to c by 2. That's the velocity of car with respect to ground along plus x direction. Okay, remember that it's along the plus x direction. We could also write it like this. All right, so it's more easy to remember. A ball is thrown from car with speed c by root 2. A ball is thrown from car with speed c by root 2. Right. So they are saying that it's thrown from the car. So we assume that this is the speed with respect to the car. So a ball, the velocity of the ball, I'll write. Velocity of the ball with respect to the car, I'll write it like this, u prime. This is the velocity, prime means velocity of the ball with respect to the car. Okay. Is ball is thrown from car with speed c by root 2. So what we know is it has speed. We are only given the speed, right? We are only given the speed. So I'll just write it like this. I'm just writing down whatever we have. The speed is given, right? So u prime, modulus u prime is equal to c by root 2. Okay. This means that we'll already write down the equation. This means that square root of ux prime plus ux prime square plus uy prime square is equal to c by root 2. These are our equations. Okay, I'm just writing down the information we get from the question. All right. Okay. Now, if you are confused, okay, it may be a bit confusing because a ball is thrown from car with speed c by root 2. Okay, you don't know whether it's with respect to ground or with respect to car. But from the next sentence, you'll understand that this velocity was about the car because the question is this: as seen from ground, the ball moves in plus y direction. Calculate the speed of ball with respect to ground. They are asking calculate the speed of the ball with respect to ground. Okay. All right, so this has to be the velocity or the speed with respect to the car. Now calculate as seen from ground, right? So from ground, we'll put it like this. U vector is equal to, okay, as seen from ground, the ball moves in plus y direction. All right, this is simply y cap because it says that it is moving in the plus y direction only. Calculate the speed of the ball with respect to ground. Okay, what is modulus of u vector? This is the question, right? This is the question. Okay. All right. So shall we do this? Is the question clear? It seems a bit complicated, okay? There are so many things involved, but we have enough equations. If you do carefully, we have enough equations to solve this completely. Okay, you may mistake this 2, root 2, all these things. Now, how do we do this now? So let's see what we can do. Okay, solution goes like this. Okay, how do we do this? We know that this thing is modulus of u vector. Is the question clear? Square root of ux square plus uy square. Remember that in this notation that we have chosen, this unprimed is with respect to ground and primed is with respect to the car. Okay. So u vector is equal to ux square plus uy, square root of ux square plus uy square. All right. Okay. How do we find ux?
ആ കാറിന്റെ വെലോസിറ്റി വിത്ത് റെസ്പെക്ട് ടു ഗ്രൗണ്ട് തന്നെയല്ലേ തന്നിട്ടുള്ളത്?
അതെ അതെ, വിത്ത് റെസ്പെക്ട് ടു ഗ്രൗണ്ട്.
അപ്പൊ നമുക്ക് uy പ്രൈമേ കണ്ടുപിടിച്ചാ പോരെ. uy പ്രൈം എന്ന് പറയുന്നത് uy into root 1 minus v square by c square divided by സെയിം ഡയറക്ഷനിൽ വരുമ്പോ 1 minus vxc by c square കൊടുത്താ പോരെ.
ഓക്കെ, അപ്പൊ അതിൽ ux പ്രൈം ഉണ്ടാവും അല്ലേ?
അല്ല, ux പ്രൈം നമ്മൾ vy അതിൽ ux പ്രൈം ഉണ്ടാവൂലേ?
Yeah, so we have to use this equation in one way or the other. I'm just thinking which is the easiest way to do this. Okay, so one option is to do this. We know the transformation. We know here, all right? Here you see that uy is equal to 0, and uz, we are not talking about uz, we are talking about a plane. All right, you see that ux is equal to 0 because we know that it's moving only along the y direction. All right, so one thing we could do is we could find ux prime from this ux using the transformation equations. All right, you can find ux prime from ux using the transformation equations. All right, and we can find uy prime from uy using this equation. All right, and put it in here, right, and substitute it in here. All right, and but we need to find uy. All right, if you substitute it in here, equate it to this, you can find uy, and then you can substitute it back here and you'll get modulus of u vector. Am I right? Okay,
Yes.
See, remember that ui is not known. Uy is not known. All right, ux is known. Am I right? Ux is known. That's equal to 0. Ux equal to 0. So this is equal to simply uy. Modulus of u vector is simply uy. Am I right? Am I right?
Yes.
Is this clear?
Yes,
Modulus
yes.
of u vector is equal to uy because it's given that it moves only along the y direction. So ux is 0. So modulus of u vector is uy. We know this. So what we just need to find uy. Okay. How do we find uy? We know ux. We know the value of ux. You know the value of ux. You find ux prime from ux. All right. And uy prime from uy. So you'll get an equation for uy. You can solve it and you will get uy. All right. So let's do that. Is this clear? All right. So we are using this equation. All right. We'll make use of this equation. Okay. So let's find ux prime. What's ux prime? Is this clear? Is this clear?
Yes, yes.
All right. So what's ux prime? What's ux prime? So the car is moving with respect, we'll write the correct equation. So that then we'll substitute. The car is moving with respect to ground along the plus x direction. So it's c by 2 x cap, right? So ux prime would be ux, right? Ux is minus or plus? This is the x component of the velocity of the ball with respect to the car, right? So you will have uxv, sorry, ux, here we'll have a v and 1 uxv by c square, right? For v, I'm not putting any subscript. We know that it's along the x direction. Tell me whether it's a plus or a minus. Just look at the situation physically and tell me whether it's a plus or a minus. Okay? Ux is the velocity of the ball with respect to the ground. All right. V is the velocity of the car with respect to ground. Velocity of the car with respect to ground. Okay. And what's ux prime? It's the velocity of the ball with respect to the car. This is the velocity of the ball with respect to the car. Right. Velocity of the ball with respect to the car. So whether it's a plus or a minus?
Minus.
Correct. All right. It's a minus sign. So the thing is that you are throwing a ball from the ground and you are looking at it from a car. Okay? So from if it has a velocity something v, say u here, and you are looking at it from a car which is moving at a speed, let's say v. From the car, if you are moving exactly at the same speed as the ball, you will see that it is 0. The relative velocity is 0. But if you are moving at some other speed v, right? With respect to the car, you will see that the velocity is u minus v. Am I right? So you just use that logic and then yeah, correct it using the relativistic thing. All right. So ux prime equal to ux minus v, 1 minus ux v by c square. Right. But again, this is kind of obvious because it's given that ux is 0. Am I right? Yeah, it's given that ux equal to 0. Right. So this means that ux prime is simply minus v. That's also kind of obvious. All right. It's also kind of obvious because you are moving in a car like this and you're looking at a ball, right? And if this is moving at a speed v, you would see that the ball is moving backwards with respect to you with the speed v, right? Okay, so the thing is, the ball is sitting at rest here, right? And on the ground, ux is 0, it's sitting at rest along the x direction. You are moving at the velocity v and looking at it. So with respect to you, with respect to this car, you'll see that the ball is moving backwards with velocity v. That's kind of obvious. You didn't have to use this formula. I'm just giving it so that things become clear. All right, what's uy prime? Uy prime is equal to uy prime is equal to, this is uy square root of 1 minus v square by c square. Am I right? Yeah, uy prime is equal to uy square root of 1 minus v square by c square divided by exactly the same factor. Right? This is transverse addition of velocities. Transverse law for addition. So transverse velocity, addition of transverse velocities. All right. It's exactly the same factor here. Ux is 0, so this factor is just 1. So uy prime is equal to uy square root of 1 minus v square by c square. Okay. And we know this v square by c square. So this is equal to uy square root of 1 minus, what's v square? Just have to be careful here. V square is c square by 4, right? So v square by c square is just, is it 1 by 4? Am I right? Is that correct? C square by 4 by c square. Yeah.
Yes.
Okay, that's correct. So this is uy square root of 3 by 4. Square root of 3 by 4. Okay. Now we have everything we need. We have everything we need. We can just substitute it here. You can just substitute it in this equation and find uy, and that would be the answer. You can substitute it here and solve it for uy, and that would be your answer. Okay, just put it all in here. Ux prime is minus v. So from this equation, we get square root of, we can just square also, right? We can also square it. So you see that you just square these things, all right? So ux prime is v minus v. So this is v square plus uy prime is uy square root of 3, uy square root of 3 by 4. So that becomes uy square. There's also square root of 3 by 4. So that's 3 by 4 uy square, and that's equal to c square by 2. Or did we make a mistake somewhere? Let's also put in v square here. Right? What's the value of v square? It's c square by 4. Okay. So you see that 3 by 4 uy square is equal to c square by 2 minus c square by 4 is c square by 4. Okay. And is that correct? Right, I think it's correct. So uy is equal to, uy square is equal to c square by 3, or uy is equal to c by root 3. Is that correct? Did I make a mistake somewhere?
Correct.
Okay. So if there's a mistake, you find it, all right? I might have missed a factor of 2 or something, I don't know. Right? So this is the answer, all right? What you're asked is the speed of the, calculate the speed of the ball with respect to ground. right? Calculate the speed of the ball with respect to ground. Since it has no x component, the speed of the ball with respect to ground is equal to c by root 3. Okay, is this clear?
Yes.
You have to check the numerics. Okay, I don't know. When I did it at home, I think I got a different answer. So you have to check, right? But this is the way we do it. So I'll just explain the steps again. I'm just writing down all the things that I have, right? The velocity of the car with respect to ground, that's given, right? And the speed of the ball with respect to the car is given. The speed of the ball with respect to car is given, that the components are not given. So we write it in this form: ux prime square plus uy prime square is equal to c by root 2. Is it correct? C by root 2. All right, c by root 2. Okay, that's there. And the thing is given that the ball moves with respect to ground only along the y direction. So that means ux equal to 0. Ux equal to 0. All right. So we know that the modulus is also equal to uy. Right. So what we are doing is that we have this equation. All right. And we know that ux equal to 0. Ux equal to 0. So you write this ux prime and uy prime in terms of ux and uy. Right, and substitute it here, you'll get an equation for uy. You solve it, and that would be your answer. Okay. Right. Okay. So such problems can be asked. So if things are confusing, what you need to do is you write down all the equations that you can construct from the information given. All right. And suppose you don't know what to do. Right? First, you write down all the equations. Okay, that or the relations that are given from the question, and you also write down these relations from Lorentz transformation, etc. And if the question is correct, you will always find enough number of equations in order to solve in between and find the unknown. Right? Usually, just questions would be to find the unknown quantity. So if the question is correct, we assume the question is correct, right? You write down all the equations that you know and what's given in the question, and you will know that there must be enough number of equations which you can solve among them and find the unknown quantity. Right? So if there are two unknowns, you should need two equations, etc. Right? So if the question is correct, and we assume the question is correct, you certainly will have enough number of equations. Right? Okay. So here the extra equation that we used is the velocity addition formula. So there are many more questions of that form, but let's just move on to the next part. Okay. I think I can give more questions as exercises. Sometimes the velocity might be given, ground might be given, and the velocity will be given at an angle. The velocity will be given at an angle. So in this case, what you have to do is that you have to just change this into components. Okay, so separate this into components and find Vx and Vy. Right, just find the components. And then you can use the method for this. This is horizontal component. This is a transverse component. You can just use the relations for horizontal and transverse velocities. Right. Okay. Now let's just get back to the Lorentz transformation equations. I'll put more questions in the exercise if I get. Okay. Let's look at the Lorentz transformation equations once again. So what we did is that we wrote down the Lorentz transformation equations. We obtained the relation between velocities in an Einstein way. Okay. And let's look at more consequences of the Lorentz transformation equation. So we'll write it in the differential form, which makes it much easier. We have got delta x prime is equal to gamma delta x minus p delta t. Okay. and delta y prime is equal to delta y, delta z prime equal to delta z, delta t prime is equal to gamma delta t minus v by c square delta x. We also wrote it using beta. We also wrote it using beta. Right? Now let's talk about simultaneity, relativity of simultaneity. Problem of simultaneity. Okay? So in the Galilean or Newtonian idea, if two events are simultaneous in one frame, every observer would agree. Right? I just say that all right, these two things happened at the same time. Okay, and everyone would agree. But in the case of relativity, that's not the case. If an observer says that two things are simultaneous, there are always other observers who say that it's not simultaneous. Right? So there are events. I explained what we mean by event. We've got A and B. Okay. So for one, if for one observer A and B happen at the same time, then there's always an observer for which A happened before B, and there are always observers for which B happened before A. Right. So ordering is not absolute in this sense. Okay. This is actually a special case, but we'll be seeing when we look at the geometry. When you look at geometry, these things might become more clear. Okay. All right. Simultaneity. Okay, so all right. So let's imagine. Okay, let's say that two events are simultaneous in frame S. Okay, this means that we already did problems which demonstrated this in a way, which means that we can take delta t is equal to 0. Right? Delta t is equal to 0, right? Okay, delta t is equal to 0. And what becomes of delta t prime? You see that delta t prime is equal to gamma, delta t is 0, so it's minus gamma v by c square delta x. Okay, v by c square delta x. Right? You see that this is not 0. This is not 0. Right? So from the Lorentz transform equation, we'll see these things much more clearly when we look at the geometry. But this we'll just discuss these things in a brief manner, and we'll see all these things from the geometrical approach, which we'll be discussing soon. Okay? So you see that if two events are simultaneous in one frame, in another frame which is moving with respect to these frames, you see that the events are not simultaneous. All right, they happen at two different times. Okay, you see that yeah, and this is the amount by which it's different. Now you can see this easily geometrically. Those I won't be giving geometric argument for all this. Suppose you have got a train like this. Suppose you have got a train and there's a light bulb at the center of it. There's a light bulb at the center of it. Okay? This train is moving at a velocity v with respect to the ground. There's an observer here. He switches on the light. He knows that light travels with the same speed in both directions, and he will see that the light hits the two ends at exactly the same time. Right, with respect to observer and the train, he will see that the light hits the two ends of the train because he has situated this bulb at the center at the same time. What about the observer on the ground? An observer on the ground see that the train is actually moving forward. Right? So light needs to travel a smaller distance toward the back and a greater distance toward the front. Right? So he'll see that the light hits here earlier and it hits there later at a later time. Right? So you see that, and the difference between them will be this thing. The difference between the time would be minus gamma v delta x by c square. Okay? I hope this is clear because this observer also says that light travels at speed c. Everyone, light travels at speed c. Okay, so this is c for all observers. So observer here and observer there, and this observer will say that the light is coming here, but the back of the train is moving towards the light bulb. Right, it's moving towards the, and since this c does not change, he will see that the light hits the back end of the train earlier than the light hits the front end. All right, so you see that the events are not simultaneous in this frame. Okay. Right. We can also talk about what's called as time dilation. Okay. So before discussing what we mean by time dilation, I'll just introduce a concept called proper time. It's a very important concept. Let's talk about what we call as the proper time. Proper time. So this proper means it's not the proper in English. It comes from the French word proper. Okay, it comes from the French word proper, and it means own. Own. Okay, so proper time actually means own time. Own time. Right. So if you are talking about a frame, we can talk about a particular kind of time. That's the own time of the frame. Right. Every frame has its own time. So proper time actually means own time. So what does that mean? This means this just the, if you take a frame, this is the time measured in a clock, which is at rest, with respect to a frame, okay, is called the proper time in that frame, proper time of that frame, or proper time associated with that frame, or simply proper time. Okay? So if you have, so what's the proper time? It's just the time elapsed on a clock which is at rest, which does not move in your frame. Okay, that's the proper time. Okay, all right. Right. Okay, so this proper time we can call it as delta T0. Delta T0. The proper time can be called as delta T0. Right? That's a time on the clock. If there is no separation, it's not moving. The clock is not moving. Okay. All right. Now you look at this equation. Look at this equation. You see that delta T prime is equal to gamma delta T minus V by C square delta X. Okay. Now if the clock is not moving in your frame, if the clock is not moving in your frame, all right, then you are looking at the clock. You're looking at the clock, which is exactly at the same point in your frame, right? This the frame is. You're looking always at the clock, which is situated at the same point on your space. So you can take delta X equal to 0, right? If delta X equal to 0, then delta T is the proper time. So you see that delta T prime is equal to gamma delta T0. Right. Delta T prime is equal to gamma delta T0. Is this clear? Okay. What does this mean? What does this mean? All right. For example, if you are looking at 1 second on the clock, 1 second on the clock. Okay. The clock is at rest here. Okay. So don't you imagine you have an electronic clock or something. Right? You have an electronic clock. Okay. Because this has a spatial separation. But just think about it. Okay. So at one moment, let's say the second hand, the second hand is here, okay, and another moment the second hand is there, all right, but the clock is not moving, all right. You are finding the time between two events. These are two events, all right, because these two events in space time. These are two events, but these two events are exactly at the same point. So you have got an electronic clock here, okay. What are the events that you're talking about? One event is that it shows, let's say, 9:45. The other event is you are taking 9:46. Okay, this is just minute, right? Okay, the two events that you're talking about are the times given by 9:45 and 9:46, right? But the clock is at exactly the same place. So what's the time separation between these two events? It's 1 minute. The time separation between these two events is 1 minute. What's the spatial separation between these two events? There's no spatial separation because the clock is at rest in that frame. The clock does not move, right? If the clock moves from one point to another, 9.45 and 9.46, then they will have a spatial separation, right? In this case, there is no spatial separation. You can take delta X equal to 0. But if you take delta X equal to 0, this is the proper time. You see that delta T prime is equal to gamma delta T0. So if you write for gamma, you see that delta T prime is equal to delta T0 divided by square root of 1 minus V square by C square. Okay. Now, which one is greater here? Delta T prime or delta T0?
Delta T0.
Is that true?
Gamma less than 1 alle.
Delta T, is it?
Gamma less than 1 ആവുമ്പോ
Gamma less than 1 ആണോ? ഇങ്ങനെ നോക്കുകയാണെങ്കിലോ? This is a bit confusing. What happens if you look at that like that? Okay, this gamma 1 by gamma is less than. This gamma is, this is 1 by gamma, right? So 1 by 1 square root of 1 minus v square, since v is less than c, okay, this is less than 1. So this quantity is less than 1. Okay. So you see that delta t prime is greater than delta t0. Delta t prime is greater than delta t0. Oh, I'm sorry, you cannot see this here, right? Camera settings had changed. 1 minus v square by c square. Okay. All right.
Time dilation varu.
Yeah, you are talking about two events, right? Exactly two same events. You see that the time interval in one frame is greater than the time interval is in measured in its own frame. Is that correct?
Yes.
I think this is correct, but we should check. It's always a bit confusing. Okay? And sometimes it's said that moving clocks run slow. Moving clocks run slow. Right? So this means that the time interval between the events, delta t, we are not talking about time, we are talking about the time interval between the events. Okay, time interval between the events. So if the time interval is less, we say that less time has elapsed on that clock. Right? So moving clocks run slow. This is not a very good thing to say because actually all clocks run at the same rate in a way. Okay. But it's usually used, all right? Moving clocks run slow, but usually all clocks run at the same rate. It's 1 second per second. In every clock, that the speed at which time moves is 1 second per second. Okay. So this is slightly misleading, but we'll see why this is misleading when we go to the geometry. If you get the geometric picture, things are much easier to understand. Right? For now, you just you can use this relation. Right? You can use this relation to solve problems. Okay? And there's an important. This quantity is very important because later you will see that proper time is a Lorentz invariant quantity. It's a very important concept. It may be asked as an you know, what do you say, option, choose the correct option. This delta t0, right? We'll show later on that this delta t0, this quantity is Lorentz invariant. Lorentz invariant. Okay, delta t0 is Lorentz invariant. It means that this quantity, delta t0, the proper time, every observer will agree between the proper time between two events. This is a very important thing. We'll see why this is important, but you have to remember that this is a Lorentz invariant quantity. Okay. All right. I hope that's clear. We can use this relation to solve problems. Okay. Also, I want you to remember that the fact that this is Lorentz invariant is a very important thing. Okay, I will see that this is I will prove that this is Lorentz invariant. It's very easy to prove, but not now. Not now. There's also length contraction. Length contraction. Okay, length contraction. Okay. So again, you can talk about a proper length. Okay, proper length. This is the length measured in a frame in which it is at rest. Okay, the length is at rest. Whatever object here is at rest. It's known as a proper time, and we can write as delta x0 or something, right? Okay. Now what we do is that let's say delta x is the okay, just a second. Let's look at this equation. Okay, let's look at this equation. Delta x prime is equal to gamma delta x minus v delta t, right? And also this thing, delta t prime is equal to gamma delta t minus v by c square delta x, right? Okay. Okay, so if you look at this, let's say delta x is the length of an object. Let's say that delta x is the length of an object as measured from frame S. Okay, delta x is the length of an object as measured from frame S. So in this frame S, this object is at rest. right? So we can call delta x equal to L0, delta x equal to L0. So you see that delta x prime is equal to gamma L0 minus V delta t. Okay, this is fine. This is fine. All right. But now, if you want to measure the length of the same object from frame S prime, right? If you need to measure the length of the object in the frame S prime, what should you do? Yeah, you have to measure the length. Okay? But when you look from S prime, this length is moving. The length is actually, imagine that you are looking at a rod of length L0. Okay, you are talking about a rod of length L0. That's in the rest frame of this. It could be a meter scale with 1 meter. It could be a meter scale with length 1 meter. Okay. So suppose you have got, this is the situation here. You have got this meter scale of length 1 meter or L0 when it is at rest, right? But when you are looking from S prime, what happens? This thing is actually moving. Right? If you're looking from S prime, okay, S prime is moving with velocity V in this direction. You see that this length is actually moving. So how do you measure the length? In order to measure the length, you have to take these coordinates. Am I right? You have to take x1 prime, x2 prime, and find x2 prime minus x1 prime. Am I right? Just find delta x prime. Just find delta x prime corresponding to the ends. But there's a catch here. There's a catch here. All right. You have to take these two coordinates at exactly the same time. If you have to take this x2 prime and x1 prime at exactly the same time, or else what happens? If you take x1 prime at some time and x2 prime at a later time, then by that time this length will have moved in your frame, right? Okay, if you take x1 prime at some time at 2 o'clock and x2 prime at 2:1, okay, after 1 second, by that time this length has already moved, so you'll get a greater length. Am I right? So if you want to find the length of an object, you have to take these coordinates at exactly the same time, right? Which means that you have to take it in such a way that delta t prime is equal to 0. Delta t prime is equal to 0. Okay, but if you put delta t prime equal to 0, you see that delta t is equal to v by c square delta x. Right? From this equation, you see that because you are taking the coordinates at exactly the same time, you have to take delta t prime equal to 0. That means delta t is equal to v by c square delta x. Am I right? Okay. So if you want, if this delta x prime has to be the length of the object in your frame, then this delta t has to be equal to this thing. All right. So you see that this means that if this delta x prime is the length, if delta x prime is equal to L, it has to be L, means if you are measuring the length, then you see that L is equal to gamma L0 minus. So the condition that it has to be at rest means that delta t has to be equal to v by c square delta x. Am I right? Yeah. Okay, so that is you, instead of delta t, you put v by c square delta x. Okay, delta x was L, so that is here there's a v square by c square, and delta x is again L0. Okay, so you see that. All right, so this is L is equal to gamma is, just write it on top. Now you just solve that part. I hope you understood why we do it like that, right? So this means L equal to 1 by square root of 1 minus v square by c square. Okay, and you can, this is gamma, you can pull this L0 outside, and this is 1 minus v square by c square. Right? So this, if you solve, if you just, this is the square of this term. So if you just solve, you see that L is equal to L0 into square root of 1 minus v square by c square. Okay, this is known as length contraction. You see that length is, what's happening here? L0 is greater than L, all right, or L is less than L0. So if you are looking at an object from a moving frame, you will see that the length is shortened. Length has shortened. This is known as the length contraction. I hope that you got the idea, right? So here we have to be very careful. The only thing that we did here is that we were a bit more careful, and we made sure that we are finding the coordinates at exactly the same time. Right? That's why we put delta t prime equal to 0 here. And then if we said that if delta x prime has to be the length of the object, then delta t has to be related to delta x in this way. We substituted and we got this equation for length contraction. This is also known as Lorentz-Fitzgerald contraction. Lorentz-Fitzgerald contraction. Okay. Okay, that's length contraction. So this question also can be asked. And I want you to remember the very important fact that the length contraction happens only in the direction of motion. The length contraction happens only in the direction of motion. Okay, not in the perpendicular direction, only in the direction of motion. It's easy to see why, but just remember that length contraction happens. Length contraction happens only in the direction of motion. Okay, no contraction in the perpendicular direction. That would lead to all sorts of paradoxes. But here, which means that if you have an object, let's say L, okay, and you are moving with an angle theta, if this object is moving with an angle theta, then the length contraction will only be in this direction. All right, you have to take this x component, or you have to take the component of this length along the direction of motion, and the contraction will only be in this direction. Okay. So such questions can be asked. We'll do problems. Okay. The length contraction is only in the direction of motion. So if there's an object like this, and you're moving with respect to that with velocity v, and you measure the object, if it is transverse to your direction of motion, you will see that the length does not contract. Okay. Length contraction is only in the direction of motion. Is this clear? Is there any doubt in these arguments? We just used the Lorentz transformation. We just looked at the consequences of Lorentz transformations. We had loss of simultaneity. We had relativity of what do you say, time dilation, the effect called what we call as time dilation. We also have length contraction. Okay, are there any questions? Conceptual or otherwise, you can ask anything, all right? Nothing? So shall we wind up?
Okay, thank you.
Okay, thank you.